Hi learners, till now we have become familiar with the time domain specifications of the control system. Time domain is divided into two portions. First is the transient response and second is the steady state response. We have learned about a number of the transient state specifications in my previous lecture. In this lecture, I am going to share the details of steady state errors and error constants. So what is steady state error? This is a closed loop type of the system. RS is the reference input or the desired output. CS is the actual output. HS is the feedback element and GS is the plant. ES is the difference between the feedback signal and the reference input, that is the desired output. So steady state error is the difference between the reference input, that is the desired output, and the actual output of the system as time t is tending to infinity. So within this particular block diagram, we can write ES divided by RS, because when we are defining the transfer function, then we can take only two variables at a time, one input variable and one output variable. So we can calculate ES upon RS from this block diagram. It will come out to be equal to 1 divided by 1 plus GS HS. Taking RS on the other side, we'll get ES is equal to RS divided by 1 plus GS HS. Now steady state error is what? Steady state error is the error between the desired output and the actual output as time t is tending to infinity. And if we apply the final value theorem, this can be written as equal to S into ES as S tending to 0. So it means that steady state error is equal to limit of S into, we substitute this value of ES in this equation. So we'll get this as the expression for the steady state error. Now comes the static error constant. Since the steady state error we have already defined, it is given as equal to limit of S into RS divided by 1 plus GSHS as S is tending to 0. So limit of, if we are taking RS as equal to 1 by S, so S into RS is 1 by S into 1 by 1 plus GSHS. Its limit as S tending to 0 is the steady state error. So this can be written as S will get cancelled, this S will get cancelled by this S, and will be left with ESS is equal to limit of S tending to 0, 1 divided by 1 plus GSHS. So it can be written as equal to 1 divided by 1 plus limit of GSHS as S tending to 0. Now this expression, limit of GSHS as S tending to 0, is termed as position error constant and it is represented as Kp. So Kp is equal to limit of GSHS as S is tending to 0. This is first of the static error constant. Then we are having the static velocity error constant. So this we have already said, we have calculated that steady state error is represented by this expression. Now let us consider a unit ramp input. So RS will be equal to 1 by S square. So we'll just substitute the value of RS over here. So this will, steady state error will be equal to S into 1 by S square. Plant is remaining the same. So it will become equal to limit of 1 divided by this. Here 1S will get cancelled. We'll be left with 1 by S into 1 plus GSHS. So S will multiplied by this. It will also get multiplied by this. When we substitute S equal to 0 here, we'll be left with this as equal to 1 divided by limit of S tending to 0, S into GSHS. So this is equal to 1 divided by KV. So KV is termed as the static velocity error constant and it is defined as limit of S GSHS as S is tending to 0. This is the second static error constant. Then we are having the static acceleration error constant. For this, we just take up RS equal to 1 divided by S cube. So we just take up a unit parabolic input applied to the system. So in such a case, steady state error is given by limit of S into RS is 1 by S cube. Plant is remaining the same. So it will be equal to this. And when we just put up this limit it will become limit of 1 divided by s square GSHS as s is tending to 0. Now this expression in the denominator as limit s is tending to 0 is termed as Ka, and this is called static acceleration constant. So we have now become familiar with three type of the error constant. Error constant for the unit step input, that is the static position error constant. For then steady state error static velocity constant, that is for the unit ramp input, and corresponding to unit parabolic input we have defined the static acceleration constant. So we just make it a revision that Kp, that is the static position error constant, its expression is this, and steady state error is equal to 1 divided by 1 plus Kp. In terms of Kp, the steady state error is given as equal to this. Then velocity error constant is represented by this expression, and the steady state error in terms of the static velocity error constant is given by this expression. Then the acceleration error constant, it is given by this expression, and the steady state error in terms of the acceleration error constant is given by this expression. Now let us consider the type 0 system, and we just take up a unit step input. We have taken a unit step input. We have taken a plant that is represented, that is containing a number of zeros and a number of poles. It is having zeros at minus 1 by T1, minus 1 by T2. Then it is having pole at minus 1 by TA, minus 1 by TB, and K is the gain of the system. Now, first of all, we'll be calculating the position error constant. So it will be given as limit of GSHS as S is tending to 0. It will be given as equal to, so GSHS is this, H is tending to 0. So it will be left with K. So steady state error will be equal to 1 divided by 1 plus Kp. So this is equal to, Kp is coming out equal to K. So it will be equal to 1 divided by 1 plus K. So steady state error is equal to 1 divided by 1 plus K. Now we have a type 0 system with unit ramp input. So in such a case, what do you do? Unit ramp input, the steady state error is given by 1 by Kv, and Kv is equal to limit of S GSHS as S is tending to 0. So this expression will get multiplied by S, and S is tending to 0. So this overall, this when we just make up the substitution, S is equal to 0 or S tending to 0, this expression will become equal to 0. So steady state error will be equal to 1 divided by 0. So it will be equal to infinity. Now we take up the type 0 system with the unit parabolic input. So for parabolic input, we are using the acceleration error constant, and acceleration error constant is limit of S square GS as S is tending to 0. We just multiply it by S square and put the limit as S tending to 0. It will come out to be Ka will come out to be 0. And for unit parabolic input, steady state error is equal to 1 divided by Ka. As Ka is equal to 0, steady state error is equal to infinity. So when the system is of 0 type, type is what is meant by the type of the system? The total number of the poles at origin define the type of the system. Like within this, we do not have any pole at the origin because we do not have any S term over here. That's why it's called a type 0 system. For a type 0 system, for a unit step input, the steady state error is this. For a unit ramp input, the steady state error is infinite. For a unit parabolic input, the steady state error is also infinite. But it is finite in the case of the unit step input. Then we take up a type 1 system. In the case of the type 1 system, when we apply a unit step input, it is a type 1 system. Be clear about the type and order of the system. Type is defined by the total number of the poles at the origin. So here we are having S to the power 1. So we are having 1 pole at the origin. That's why it's a type 1 system. So for type 1 system, if we are having a unit step input, then the steady state error is equal to 1 divided by 1 plus Kp. Kp will be limit of GSHS as S is tending to 0. So we'll just put it over here. So when we substitute limit of s tending to 0 here, so this 0 will make this expression infinite. So Kp will become infinite and steady state error will become equal to 0. And when we are using a unit ramp input, so again, this s that we have in the transfer function, it will get cancelled by this s and will be left with kv as equal to k, and steady state error is equal to 1 divided by kv. Then type 1 system with the unit parabolic input. So this is, for this we calculate the acceleration error constant. Since it's a type 1 system, 1s will get cancelled over here, but still we are left with 1s over here. That will make the value of acceleration constant as equal to 0. So when acceleration constant is 0, it means the steady state error is equal to infinity. So this is the type 1 system. So for the type 1 system, the steady state error is 0 for the unit step input. This is 1 by k for unit ramp input, and this is equal to infinite for the unit parabolic input. Then we are having the type 2 system. Within type 2 system, we are having 2 poles at the origin. Then again, we apply the unit step input. So steady state error will be equal to 1 divided by 1 plus Kp, and Kp in such a case is coming out to be because we are having s tending to 0, and so it is coming out to be equal to infinity. So as Kp is becoming infinity, steady state error is becoming equal to 0. Similarly, for the unit ramp input, we will be having Kv, and since we are having 2 poles at the origin, so 1 pole will get cancelled, but still we are left with 1s in the denominator. That will make up this expression infinite as s is tending to 0. So Kv is equal to infinity, means that steady state error in this case is equal to 0. Then we take up a unit parabolic input and the system is type 2. So in this case, this s square will get cancelled with this. When we substitute limit of s tending to 0, then we'll get a finite value that will be equal to Ka. So steady state error in this case will also become finite, that is equal to 1 divided by Ka. If we have a comparison between the steady state errors for type 0, type 1 and type 2 system, we can very well see that steady state error is 1 divided by 1 plus Kp. Then for the type 0 system, and this is for this unit step input, and this is 0 for type 1 system, and this is again 0 for type 2 system. So it means that if we look at this table, we can very well see that the steady state error for unit step, unit ramp, and unit parabolic input, these are the 3 cases here. First case, in this, in type 0 system, error is this. Type 1 system, error is 0. Type 2 system, error is 0. Then for the the unit ramp input, for type 0 system, error is infinite. For type 1 system, error is 1 by kV, and for type 2 system, error is 0. And for the unit parabolic input, the steady state error for the type 0 system is infinite. For type 1 system, it is again infinite. For type 2 system, it is finite, that is equal to 1 divided by Ka. So we can very well observe from here that as the type of the system is increasing, then it is resulting into the reduction in the reduction in the steady state error, because we can see that as the type is increasing, the steady state error is also becoming less. Here it is 1 divided by 1 plus Kp, here it is 0, here it is 0. Then type is increasing. Then here it was infinity, here it is 1 by Kv. Further type increase, it becomes equal to 0. Acceleration, it is for the unit parabolic input. Type 0, for type 0 system, the error, steady state error was infinite. For type 1 system, it was infinite, but for type 2 system, it becomes equal to finite one. So it means that as the type of the system is increasing, then we are getting the decrease in the steady state error. It means that it apparently because the type of the system is increasing, and corresponding to that, the steady state error is also decreasing. So also the steady state error can also be reduced by increasing the value of Kp, Kv, and Ka. It seems that we can reduce the value of the steady state error by increasing the value of Kp, because it is inversely proportional to these constants. But this is not a solution, because if these gains or the error constants are kept at very high value, then they may result oscillations within the system, thereby making the system response oscillatory, and the system may become unstable. So the we have to just make up a balance between the steady state error to be achieved and the overall gain of the system. So that's all for today, because within this lecture we have just learned about one more specification that is related to the time domain, that is related to the steady state response, time response, and that is the steady state error. And then we have learned about the various static error constant and their relation to the steady state error, and relation of the steady state error to the type of the system. So thank you for being with me and listening to me with patience. Thank you so much.